everyone, and welcome back. Today we're going to be continuing our exploration of linear algebra and continue focusing on a couple applications that are very important in daily life. And the application we're going to be focused on today is Markov chains. Now, there's a lot of theory associated to Markov chains and also something called Markov processes, but we'll leave that more for a probability audience and just focus on the surface understanding of what a Markov chain is and how matrices, vectors, eigenvalues, and eigenvectors actually play an important part in this discussion. So let's give a brief introduction to this concept. So let's start off by assuming that you can only take one of a finite number of states. And let's abbreviate those states as SK, where K ranges from 1 to n. We can, of course, increase this finite set into an uncountably infinite set or even a countably infinite set, but we'll just keep things finite just for today. So the set of all states that we can have is going to be referred to as the state space. Not very important for today, but that's just some terminology that's commonly used. And let's assume that K actually represents the time for which you can have. So let's actually change these subscripts, although some people will switch these around. And let's assume that this K is actually T, right? So T represents time and K represents the state ID that we're in. So let xt represent the probabilities, and if you know anything about probabilities, keep in mind that probabilities can only take continuous values between the closed real intervals 0 to 1, and let's assume that that is the probability of being in each of those states at that particular time, and again, let's assume that that represents time t. So let's give a quick example of sort of what we're laying out here. So let's assume that our state space S is going to be equal to, let's assume we're talking about moods. So for example, we have a happy mood, we have a neutral mood, and let's assume that we also have a sad mood, and let's assume that that practically spans the set of moods, right? So in this case, that the cardinality of our state space, or I'm going to abbreviate that as NS, is obviously going to be equal to 3. And we're going to be abbreviating happy as state 1, neutral as state 2, and sad as state 3. So let's assume that we look at the initial probability, in particular at time t is equal to 0. So when t is equal to 0, we're either going to be happy, neutral, or sad. So sometimes x0 is called our initial state vector, right? So let's assume that at time t is equal to 0, we actually start happy. So that means the probability at time t is equal to 0 that we're happy is going to be equal to 1. And if we're happy at time t is equal to 0, that means we're definitely not neutral and we're definitely not sad. So the probabilities for each of the others are going to be equal to 0. Obviously, if you start in the neutral state or the sad state, then those would be 1 respectively and everything else 0. But let's assume that this is where we start. All right? So let's assume that after some time, we have, for example, at time t is equal to 8, what's the probability that, for example, we are happy? Obviously, you know, maybe something bad happens and the probability that we're happy at time t is equal to 8 is like 10%. Let's assume that the probability that we're neutral at time t is equal to 8 is 10%. And obviously, since this is a probability vector, then the probability that we are sad at time t is equal to 8 obviously would be the number that sums up to 1 for across those values, right? So this number here can be interpreted as the probability of being sad at time t is equal to 8. And keep in mind, we can also interpret this as probability of being in state 3 at t is equal to 8. All right, so how can we interpret or give a little bit of generality to these vectors? So obviously the sum from I is equal to 1 to 3, or generally speaking, the number of states in this vector. Let's assume that this is, for example, xt, and let's assume this is the kth element, or actually the ith element, right? So this is obviously a column sum, this should be equal to 1, and this obviously has to be true for all t in n union 0, right? So obviously if this is the case, and also another property has to be satisfied, is that each of these elements, xti, must also belong to 0, 1, right? So that means that xt is a probability a probability vector. Right, so the vector of entries that sum up to 1 and also all belong to the interval, closed interval 0 to 1. Right, so that's what we call the state vector. Now let's talk about probability transition matrices. For example, is it possible to transition from happy to sad, or sad to happy, neutral to sad, and so on. So let's look at, or actually let's first off state what we're going to describe in terms of notation. So let's suppose that Pij corresponds to the probability of transitioning to state I from state J. Now, to Si from state J. So J is where we are, I is where we are going. Now, this is just a convention. Some people will also write this as the probability transitioning from Si to state J, but again, as long as you know which convention you're working with, that's all that matters, right? But we're going to be keeping this convention because I feel that it's a little bit more natural or nicer to work with, but technically they're all equivalent as long as you adjust your notation and your formulas accordingly. So how many states do we have here, right? So what is the range of I to J? So if we work with the same exact example, happy, neutral, sad, then practically what we have here is we have the happy state, we have the neutral state, and we also have the sad state located down here, right? So we have, for example, state 1, state 2, and also state 3. So let's assume that we want to transition from happy to neutral. So if we take this convention, that's going to be P of, so we're going to Si from Sj. So this is going to be equal to P to 1. And keep in mind, direction does matter here. So this is the probability of going from happy to neutral. We could also go from happy to sad, so that's going to be equal to P31, and we could also transition from happy to happy. Well, technically that's not a transition, it's pretty much staying fixed. That would be P11. Right? So we have P11, P21, P31. That's the probabilities of transitioning from happy to the others, or to the others from happy. So we clearly see that P11 plus P21 plus P31 must be equal to 1, because those are all of the states for which they could be. Keep in mind it's possible that it's impossible to transition from happy to sad instantaneously, so that might be equal to 0, but technically speaking 0 does belong to the interval 0 to 1, so that is perfectly valid. Now, let's fill out this chart with the rest of them. For example, we can go from neutral to happy, so that's going to be P12. We can go from neutral to sad, so that's going to be P32. And we can also stay at neutral, so that's going to be P22. We can also go from sad to happy, that's going to be P13. We can go from sad to neutral, that's going to be P23, and we can also stay sad, so it's going to be P33. So if we continue this convention, what are we going to have? So we're going to have P12 plus P22 plus P32 will be equal to 1. We're also going to have P13 plus P23 plus P33 must be equal to 1 as well. So practically what you have here is probability vectors, and by this convention, the probabilities are going to be located across the sum, right? So it's, for example, the first row, first column, second row, first column, third row, first column. So that's the sum across the column, so we still have probability column vectors. So we can generalize this as the sum from I is equal to 1 to ns of Pij is equal to 1. And this is obviously going to be a column sum once we place all those matrix elements inside a matrix. So now let us formally define the matrix that's going to contain all of these Pij values. So let's look at the first definition of today. So let's assume that P is going to be a square matrix of dimensions ns by ns, so the number of states by the number of states and our state vector. And let's assume that the elements are represented by Pij, and let's assume that P maps the vector space Rns to Rns, where that restriction of that set R is restricted to closed intervals 0 to 1. So all of the elements in the vector must belong to 0, 1 for both the domain and the codomain. Then P is called a left stochastic matrix. So this is where the convention sort of comes into play, because remember that we're assuming that the values of those probabilities belong to 0, 1, and the sum of the column, because keep in mind this is the column sum, is taken to be the convention, right? So for example, if you want your probabilities to be row probability vectors, that would be called a right stochastic matrix. Right? But we say that this matrix P is a left stochastic matrix if all of the values are probabilities in the matrix and the sum across all of the columns is equal to 1. All right? So let's look at our example and see if we can build a left or just a stochastic matrix for our system. So obviously, since we're working with 3 states, happy, sad, and neutral, we're going to have a 3 by 3 matrix, and the sum across the columns must be equal to 1. So what is that going to be? So let's assume that our first vector is 0.5, 0.3, 0.2. That obviously sums up to 1. And let's assume that we have 0.6, 0.3. The last should be obviously 0.1. And if we have 0.3 and 0.2, which should be the middle element, you should know that that's just going to be equal to 0.5. And I probably should have made these all different colors. Let's just change that middle column into green. Let's say 0.6, 0.3, and 0.1. So there's lots of colors for happiness. All right. So what are these probabilities going to be associated to? So the first column is going to be the probabilities of transitions from state 1. The second column is going to be the transition probabilities from state 2. And the last column is going to be the transition probabilities, transitions from state 3. Right? So some people will also refer to this as a transition or a left transition probability matrix. Probability matrix. So left probability matrix. So what is 0.5? So that's the probability of transitioning from S1 to S1. 0.3 is the probability of transitioning from S1 to S2. This 0.2 is the probability of transitioning from S1 to S3. Similarly, if I were to focus on this 0.5, that's the probability of transitioning from S3 to S2. So the probability of transitioning from sad to neutral. All right, so that's our transition probability matrix. Now, if you have that the columns and the sums all sum up to 1, some people will call that a doubly stochastic probability matrix, but that's for another day, but I should at least introduce you to the terminology just in case you do encounter it in the future. All right, so let's assume that we have our initial state vector, right? So let's suppose that x, which is 1, 0, 0, is our initial state, which in this case is happy, vector. Now let's build or connect this happy state vector and also our probability stochastic matrix. So next definition, and this definition is practically the highlight. So let's assume that k belongs to the natural numbers unionized with 0. Then x0 is called the initial state vector, so you already know. And we're going to denote xk plus 1. So the state at time k plus 1, we're going to define this to be equal to p times xk. And obviously this is going to hold for k greater than or equal to 0. So once we define this initial state vector and define this recursiveness of the states at time t is equal to k, then the object defined by C, which is going to be a pair of P, a probability matrix, and the sequence xk, where k ranges from 0 to infinity, is known as a discrete time I'm going to put this in parentheses because we're not going to continue or discuss the continuous time case, but it's called a Markov chain, a discrete time Markov chain. And the only reason that it's discrete time is because we're assuming that k belongs to this discrete, cannibally infinite step. Right, so that's going to be a discrete time Markov chain. So what exactly are we going to do with this? So we know where we start, and we know the probability of transitioning from each of the states to the next state. So let's look at what x1 would be from this definition. So x1 by definition would be equal to p times x0. So that's going to be equal to our probability matrix times 1, 0, 0. So let's recall what those values are. So 0.5, 0.6, 0.3, and then we have 0.3, 0.3, 0.5, and then 0.2, 0.1, and 0.2. So if we multiply these things out, what are we going to have? So we're going to have row 1 times column 1 of that little vector, which is obviously just going to be equal to 0.5 plus 0 plus 0. And then we're going to take the next value and multiply by that vector, and we're just going to be equal to the first element in that row, which is 0.3. And then we're going to be multiplying that by that column vector, and we're obviously still going to get 0.2, right? Which is just equal to, notice, the first column, right? Now, obviously, it really depends on what that initial state vector was, because if that initial state vector was that we were started in the neutral state, then we multiply p by x0, we would actually just get column 2. And if we started in the sad state, then we would get column 3. So this first vector for x1 is actually pretty trivial because it's just associated to the column for which the state we initialize is being set in. Now, a very interesting thing is if we sum up all the values of x1, we still get 1, right? So if we sum across all values of I, where I ranges from 1 to 3, we still get 1, so this is still a probability vector, and you should be able to verify that as long as x0 is a probability vector and p is a stochastic matrix or a probability matrix, then x1, x2, x3, x4 down to x infinity will also be probability vectors as well. So how are we going to interpret these probabilities in x1? So if we look at these numbers, for example, let's focus on 0.2. 0.2 is the probability of being sad. So that's the probability of being sad or being in state 3 at time t is equal to 1, right? That's the 1 subscript here. If we start in the happy state, right, i.e. state 1. So this is the probability of being sad after 1 day, assuming that we start in state, the happy state, state 1, on day 0. Right, so that's how you can interpret 0.2 and also the other numbers as well. Now, what's a little bit more interesting, because this is not exactly obvious, what about t is equal to 2? Right, so what's the probability of being in happy state after 2 days, assuming that we start off in the happy state? What about neutral? What about sad? What's the probability of being in those states? So at t is equal to 2, by definition, that's going to be equal to p times x1. But x1, we already know, is just going to be equal to p times x0. So p times p is equal to p squared, because we know matrix multiplication is associative. So we just have p squared times x0. Right? So what is that going to be? So if we do that multiplication out, we can obviously multiply p by x1 or calculate the matrix p squared and multiply it by x0. In either case, we're going to get the same exact answer, and we're actually going to get 0.49, 0.34, and 0.17. Right? So again, how do we interpret these numbers? So let's focus on, for example, 0.34. So 0.34 is the probability of being neutral, or the probability of being in state 2 at time t is equal to 2, the subscript, provided we start happy at time t is equal to 0. Right? So that's how, again, how we interpret these probabilities in this probability vector. Okay, so let's see if we can generalize this. So obviously x3 will be equal to p times x2, which will be equal to p times x1, which is going to be p times p times p of x0. So using mathematical induction, you should be able to see a very nice pattern here. In particular, xn is going to be equal to p to the power of n times x0. P is a square matrix, so exponentiation is clearly well defined, provided that n is a natural number or even 0. All right? So that's a very important thing. That's pretty easy to see here. Now let's actually look at something very interesting about this, because obviously we have a sequence of powers of matrices, right? That's practically what a Markov chain is. So if we look at x0, which we start off as 1, 0, 0, and then we were easy to calculate x1, which is just column 1, which was 0.5, 0.3, 0.2, and we can easily calculate x2, as we've already mentioned, just multiplying this vector by p, which came out to 0.49, 0.34, and 0.17. So what if you were to do x3, x4, x5, x50, x5 million? Moreover, what about x infinity? So what would x infinity be? So a natural way of defining this is going to be equal to the limit as n goes to infinity of Pn x0. So you can actually find, because this is actually just going to be practically a geometric series, what you're actually going to find is this is going to be equal to 1/2, 1/3, 1/6, right? And I'm actually going to call this vector q, because this is a very, very important vector. Obviously, 1/2 plus 1/3 plus 1/6 is equal to 1. So obviously this is a probability vector. Right? But another interesting thing about this is the following. So if you multiply p times this vector q, you're actually just going to get q. Also, if you do p squared times q, you're also going to get q. And this is going to continue on and on and on. So if you notice here, what you're going to have is that pq is equal to 1 times q. And if you know anything about eigenvalues and eigenvectors, this should look very, very familiar to you, because this is practically just p lambda, and this is going to be equal to, or pu is equal to, actually let's call it px is equal to lambda x. Right? So we see here that this vector q, assuming that you can prove that this identity is indeed true, we see that q is an eigenvector. It's an eigenvector for p, and its eigenvalue is 1. Now, is that by chance? Because this vector that this sequence or this Markov chain converges to might be pretty useful, because eventually practically the probability of transitioning from one state to another is fixed for all time, infinity, and after, right? So let's look at a little bit of theory that's behind that. So who exactly is this vector q that sort of comes up by limiting this iteration of p onto our initial state vector x0? So we call that vector a steady state vector. Some people will also call it an equilibrium vector, because it pretty much is not changing. It's steady in terms of its state. So we have some state q after some time t. It could be finite, it could be infinite, we don't know. And it pretty much stays steady, even though the probabilities of transitioning from one state to another do remain fixed, and it's possible to change from one state to another. But the probabilities of transitioning from one state to another, regardless of the initial state, stays fixed, right? So that's pretty much what a steady state equilibrium vector is, right? And again, this P is a stochastic or probability matrix, and we're assuming that it's a left stochastic matrix. So based upon the previous example, we clearly see that the vector 1/2, 1/3, 1/6 is a steady state vector for our left stochastic matrix 0.5, 0.6, 0.3, 0.3, 0.3, 0.5, 0.2, 1, and 2. 2, 1, and 2. But we were only able to get it by iterating that exponentiation process potentially infinitely many times. So the first question we need to figure out is this q unique? Well, if it is the value of a limiting process Since limits are unique, then the vector associated to that limit must also be unique. So that's not actually too hard to prove. Because if once you can establish its existence, you can just use a quick proof by contradiction to show that, if you do assume 2, those 2 will always be equal and hence uniqueness is guaranteed. Right? But what if we don't want to iterate that process potentially infinitely many times, but we still want to know what the steady state vector of that probability matrix actually is? So if we look at our particular example again, and we do the determinant of that associated stochastic matrix P, we can find that the determinant is non-zero, which obviously means that this is invertible. Now, I'm not going to go into a discussion of what that inverse of a stochastic matrix is, but that would give a little bit of an interesting journey to explore on your own if you do have the time to. But what's more important, if the determinant is non-zero, that means 0 is not an eigenvalue for that, right? So if we find the characteristic polynomial of this matrix P, which is obviously going to be a function or a polynomial of variable lambda, one can actually find for our particular stochastic matrix that's going to be equal to negative 1 over 50 times lambda minus 1 times 50 lambda squared plus 1 once you factor that cubic out. And from here, we see that we're going to have 2 complex eigenvalues here, or 2 non-real eigenvalues, and we have this very nice eigenvalue 1, right? So we can find that lambda 1 will be equal to 1, and lambda 2 and 3 will be equal to plus or minus the square root of 2 over 10 once you simplify the square root of 1 over 50. So that gives us our eigenvalues, and notice that we have one very beautiful eigenvalue here, and that's the eigenvalue of 1. Now, if you were to build another stochastic matrix, will 1 still be an eigenvalue for that? The answer, take a guess, yes. So let's assume that P is a stochastic matrix. Left or right, actually, it doesn't really change this result. So this is actually very nice, right? So if P is a stochastic matrix, then the first result, that's actually not too hard to prove, is that 1 is always an eigenvalue. 1 is always an eigenvalue. And in terms of the other eigenvalues, for example, this plus or minus root 2 over 10, if lambda is an eigenvalue of P, then the absolute value or the magnitude of that eigenvalue will always be less than or equal to 1. So if you know anything about the Gershgorn circle theorem for eigenvalues, this actually might ring a bell. So for example, if we have the real part of lambda here, and the imaginary part of lambda there, regardless of the size of the stochastic matrix, all of its eigenvalues will be located here in terms of its magnitude. So that's actually pretty interesting. So those are some important theorems that you definitely should know about eigenvalues, and the proof of them is actually not too difficult. So what about eigenvectors? So what about eigenvectors? Right. So if we look at the eigenvectors for our example, if we look at the eigenvector for lambda is equal to 1, you can obviously find, with minimal difficulty, the vector c, 3, 2, 1. Right? There are 2 other eigenvectors, but I don't really care about them because they're associated to pure imaginary parts. But this one is actually pretty interesting. So what is the eigenvector? So this is one of them, but keep in mind c is a scalar. There are infinitely many eigenvectors. Again, don't choose c is equal to 0. But let's assume that I want to find the probability eigenvector associated to lambda is equal to 1. And obviously I can always find it because all these constants are the same sign. They're all either all positive or all negative. Either one is perfectly okay. So if I want this to be a probability vector, then I want 3c plus 2c plus 1c to be equal to 1. I want the sum to be all 1s. And once I do that, I can find that c is just going to be equal to the reciprocal of the sum of those entries, 3 plus 2 plus 1, which is going to be equal to 1 over 6. So I can rewrite this eigenvector for lambda is equal to 1 to be equal to any constant multiple. Again, c is arbitrary here in terms of its uses. So 3 divided by 6 is going to be 1/2. 2 divided by 6 is going to be 1/3. And then 1 divided by 6 is just going to be 1/6. So we have this vector here. So question, does this vector look familiar? It should. That is our steady state vector. So you actually don't need to iterate that stochastic matrix onto our initial condition in order to find it. Actually, all you have to do is find the eigenvector, the probability eigenvector associated to the eigenvalue 1. Right? So that's actually very, very beautiful. So there are several other things that you can find, but let me list out a couple more very important results that are associated to eigenvectors for stochastic matrices. So let's list it as here. So let's assume that P is a stochastic matrix, and let's assume it has a steady state vector whose name is Q. Then all the following are also true. So the first property that you definitely should know is that the limit as n goes to infinity of Pm, which I'm going to denote as P star, will also be a stochastic matrix. So if you do P to the power of n, eventually it will converge to a matrix. Now, what is so special about the matrix, P star? All columns, and let's assume that this is a left stochastic matrix, all columns of P star are Q. Now that might seem very strange actually, but that's actually what it comes out to, which is actually kind of interesting, at least to me. And 2.3, the probability E vector of P associated to the eigenvalue lambda is equal to 1 for P is precisely who? Q. Right? Now in terms of proofs for the eigenvalue theorems, they're actually pretty interesting. The proof of 2.1 isn't too bad as long as you know something about spans of column vectors. The proof of the third one probably would be the second most difficult, and this theorem is actually pretty interesting but also not too difficult as well, as long as you remember that all of the columns entries are less than 1, and all of the eigenvalues cardinalities is less than or equal to 1. So you'll have a lot of tools to sort of play around there, right? But those are some of the basics that you definitely should know when it comes to Markov chains, and that just gives you a nice little introduction to Markov processes. Of course, if you want to learn more about Markov processes, learn a little bit of probability, and we'll see you in that particular discussion. But until then, I hope you enjoyed this video. Take care.